Hey everyone, how are we doing? I had to take out my contacts again. Oh my gosh, I need those new contacts in. Reed, good to see you here. What should we do, Reed? What should we study? What should we talk about? I'm gonna get my hair cut today. You never know. When do they have a hair appointment? It's getting so long. So long. Like look at this. Look at this stuff going on right here. Good to see you too, Reed. Gosh, my hair is just like crazy long. What happened? What happened? I haven't gotten it cut in like a year. Craziness. It'll be March tomorrow, March 2023. Gosh, time is flying by. What should we do? Woo! Disappear, reappear. Covered a lot yesterday. Talk about some 320, talk about some 201, whatever people want to talk about. We got the exam today, and a big thing, big thing, is the review pages. So when describing distributions like shape, center, spread, and spreads just for univariate, yeah, let's talk about that real quick. Yeah, let's talk about, let me bring that over here. And let's talk about Chapter 2, Univariate Quantitative Data. Stat 201. Good to see you here, Jesse. Chapter 2, Univariate Quantitative Data. Okay, let's do it. So shape, center, spread only applies to univariate quantitative. What are some ways we can display univariate quantitative? That means I ask someone like their age, or ask them their weight, or ask them their height, or I ask them their GPA. These are all questions that are univariate quantitative. So what are some ways? You're meant to look at the screen and like repeat back answers now. Like what are ways if we ask people their age? Histogram, number one way right there. Histogram, box plot are great ways right there. And what's really great about Jump, so I do like Jump, I like R better as people know, is when we do stuff in Jump, if you make a histogram and Jump, you also get a box plot. Stem and leaf, yeah. So all these ways right here, if we go to analyze and we go to the distribution of people's ages and we make a distribution, very clearly this is what, now be careful, very clearly this is what skewed. Very clearly this is what skewed. I catch people off guard with this one. Very clearly this is what skewed. People get tricked with this one all the time. Right skewed. Great job, Haley and Reed right there. Right to the high, left to low, whatever way the tail goes. The common mistake with this is just to bring it down like this. There we go. A mirror image, so I got to remember which way. Bring it down like that. But then the number line will be reversed. We mirror right to the high, left to the low. So when you look at this, now it's all scrunched up right there. Please ask any questions you have. It is right skewed right there because you can see it goes to the right. So in the previous format, you had to look and say, oh, it's being pulled to the right side, and the mean is going to be higher than the median. So if you look at the median right here of 20, the mean is a little bit higher. Interesting, it's got that strong peak. We can also find out the skewness. This is not required for 201, but you can go here and actually find the skewness. A skewness of 0 indicates that it's more symmetric. A positive skew, ooh, I'm shocked that the mean and median are that close with that strong of skew because that is very skewed. So this is extremely right skewed, and that is positive skew, right to the high, left to the low. Now, we need to know the proper, let's go with the proper spread for this. Quote from me the proper spread. What is the proper spread for this? What is the proper spread for this? So what is the proper measure of spread, and cite for me the numeric value? We're just doing question after question. It is the IQR. The IQR stands for the range of the interquarters, the interquartile range. I meaning inter and Q quarters. And it is 2. And Reed got that right here. And great job, Reed, right there. Oops. Well, I'm just clicking all the wrong buttons. So right here is the interquartile range going from Q1, which is the first quarter, 1/4 of the data, to Q3. Just think of 1/4, 25% of the data, 3/4, 75% of the data. And the range is 2 right there. If you want to do a quick calculation, where would outliers begin? So where would high and low outliers begin for the box plot? So we have to go here. So try to solve this while I solve it. The IQR is 2. Here's where Q3 is at. Here's where Q1 is at. So where would high and low outliers begin? Where would high and low outliers begin? Yeah, that is right? Wow, Jesse, I had it wrong in my head. That is correct. I had a wrong number. It's going to be, because we're going to go plus 1.5 IQRs. And that would actually be plus 3 because 1.5 times this is 3. So we're just going to substitute in 3 right here. And so that's 21 plus 3, and then 19 minus 3. So there are no low outliers. There was no one unusually young for college, which don't worry, I was in college at like 24. So that's actually where, I mean, I was 25. I don't know. Nothing wrong with being, but it's like, oh, this is not usual. And 24 right here. Now, you don't see these. You don't see where the fences are in the box plot because the fences are an invisible boundary. But right here are individuals probably at 25 years old. You see right there. So 24 is not an unusual occurrence. These are people who are 24 right here. And this is discrete data. It looks like it was no decimals because you see like 25, 26, 27, 28. Maybe we have no 29, 30-year-olds. But these are the start of outliers right here, and then they become more extreme. There's some sort of coloring going on where I've colored the rows. So let's clear the row states, and there we go. So we see where the outliers would begin, and the proper measure of center is going to be the median. Also take note that when you use the median and IQR, the median and IQR are right next to each other. So if you have any jump output on the test, you can tell that the median and the IQR are paired together. You can also tell that the mean and standard deviation are paired together, and that's for more symmetric normal data. So the first thing we do when we talk about shape center spread is we talk about the shape. This is very, very, very right skewed. So we are going to use the ones that are not impacted. Like we have measures of center, median, and measures of spread IQR that are based on positions. So if there's extreme values over here, it's not going to impact the middle number. If that number becomes 1 billion, the middle number is still in the same position, but the mean would be drastically inflated. So with this right here, we can make other graphics, and these are the ones Jesse was mentioning. We don't make these ones that often. We make stem and leaves right here. Here's a stem and leaf plot. Now, stem and leaves are good for smaller data sets because you can see the numbers. This is really bad for bigger data sets because you can see the numbers. So we're not a big fan of stem and leaves when it comes to big data sets. Dot plot would just literally have dots right here. If you just turn these to dots, I'll show you visually. Dot plot is not that fun. Not a big fan of them. It's univariate, quantitative, but each of these would just be dots. You just have dots right there. So not a big fan of those. Hey, Ford, good to see you again. Haven't seen you in a while, Ford. So there's dot plots. And what's really cool is we can do all this over here in R. So if we have a data set, and please ask more questions because I'm just showing how this can all be done. Here's a numeric vector on the miles per gallon of cars. So I can take this right here and go to a histogram of that. And there's a histogram of it. I can go to a box plot of it. There's a box plot of it. We can make them more purdy. Hey, Jesse, good to see you. Checking the points. And Tyler, good to see you. Guess what we can do right here? But you can't guess what that's going to do. That's a stem and leaf right there of the same data. So all of these, can we do dot plot? No, it doesn't know dot plot. Let me see if there's a dot plot in R. Dot plot in R. Someone's going to have an example of how to do a dot plot. They're doing different kinds of dot plots than when we do. We'll look one more second right here on this. Oh, there's a GG dot plot. Okay. Okay, here we go. It's, here we go. Okay. Try this real quick. Need to load library ggplot. And the data set is empty cars. And we don't want to do we just want to do the y variable this. And the y variable is mpg. And then we run the graphic. It's mad. It's all kinds of mad. There we go. Let's doing it. It's only 6-cylinder cars. Huh. Not a big fit. It's bivariate right now, which is not how we should make it, but dot plots just show you dots. Is Mubot here? Oh, let's wake up Mubot and give some points. Oh, I've been giving out points and Mubot's not awake. Oh my gosh, he destroyed the universe. Can you go over some examples of different samples and their sample frames? Yeah, we could do samples and sample frames. Yep. Dot plots, not the biggest fan of. This is actually, this is more of a scatter plot, right? No, well, it is kind of y variable. X, yeah, I don't usually make dot plots. Not a big fan of them. Not a big fan of dot plots. Histograms, box plots, stem and leaves are your real go-tos right there, the ones we mainly use in statistics. And we've got lots of great ways to plot those. As we just saw in jump right here, plotting out them, the jump output's going to give you the box plot above the histogram. So pretty good right there. Hey, Colin, good to see you here. Guess who's starting to use SQL and S and R now? That is awesome. Of course. And I'm glad we're corresponding on this. And sorry we've been playing phone tag right there. But that's awesome, Colin, right there. Colin, excellent work. I'm gonna drink some coffee. I got the glasses on today. Drinking all my coffee right here. So with this, let's do some examples of sample frames, samples, and all that good stuff. So this is chapter 1, sampling techniques. Statua 1, chapter 1, sampling. Okay. So when it comes, and Haley, good to see you here. When it comes to sampling, you need note cards. You need note cards. What is the number one way to get the questions right on sampling? You can pause the screen when I go back over these because they're notes we took yesterday. But what is the number one way to get these things right? Make your own examples, make your own note cards, know how to define them. So take screenshots of these right here. I've got the definitions and different things right here. We did some examples yesterday. One thing I didn't put here yesterday was the sample frame. I totally forgot that one. Sample frame. So the sample frame is everything we have access to sample. Now, this is what usually confuses people is like, what's the difference between your sample and your sample frame? So think about this. If I go to the dorms, let's say I go to Stokely at 10 p.m. tonight to talk to students about dining options, what is my sample frame? So let's say, yeah, we'll do that right here, Haley. Good questions. We'll do some examples of that. So if I go to Stokely at 10 p.m. tonight, what is my sample frame? So I go over to Stokely and talk to students about dining options. I'm like, hey, so they just Stokely just closed the dining hall. Did they close it at 10 p.m.? I don't know. They closed it at 10 p.m. Just want to hear your experiences about dining. People in Stokely at 10 p.m. Exactly, which might not be Stokely. I think is the athletics dorm. So we might have more athletes than we usually have. It's also right near one of the dining hall options, so people are going to be more towards their opinions on that dining hall option. So it's not really a good way to sample because you're going to get a biased sample that's more towards the late night crowd and people on campus and people who are eating at Stokely and maybe more athletes. Nothing wrong with athletes, but we want a representative sample. So the sample is what we're going to take data from. Now, the sample frame are anyone we could speak to. Hey, Adam, good to see you here. We want to understand the population of all students who choose to go to dining options at UT. So in this sort of theoretical example, Brian wants to understand students who eat at UT, like eat on campus. He's going to collect data on them by taking a sample of students, and he needs to find a way to make a good sample frame. So a really good way of doing this would say, let's say there are 5 dining halls on campus. And we'll put here PCB's gone. Stokely, I think it's gone, right? Stokely, University Center, West Campus, so they'll call it, and then we'll just say the others. So we've got 5 dining hall options. So now, with these 5 dining hall options, we are going to take a sample of 50 students from breakfast, lunch, and dinner from the 5 dining halls, i.e., we will have a sample from breakfast from each, and lunch from each, and dinner from each. Now, can anyone identify what kind of sampling method this is? Can anyone identify what kind of sampling method this is? This is a tricky one. It's not simple random sample. So when you go, and good answer right there. We got through all those points. Mubot hasn't been giving valid points lately. It's not simple random sample. Simple random sample is when you give everything a number and everyone has an equal likely chance to be. It is a multi-stage. It is a multi-stage. What kind of multi-stage? It is multi-stage. I wrote a really tricky one. It is a multi-stage. We want to understand all UT students who choose dining. We're going to take samples from the different dining halls, and we're going to do it during different times. So we'll see what is the multi-stage? It's a 2 multi-stage. It is stratified. And what's the other one? What are we stratifying by? What are we stratifying by? So how are we acknowledging differences and sampling according to that difference? So stratifying means you acknowledge a difference and then you sample according to that difference. Time and place. So the multi-stage is what? Time and place. So the multi-stage is what? Reads onto something. Good guess, Adam, right there. Reads onto something. Time and place. So the multi-stage is what? You see it? I wrote a tricky one. Someone's going to see it and be like, oh. The multi-stage is what? I'm going to give it another 10 seconds. I want someone to see it and be like, okay. Well, so how would you say it? It's not systematic, because systematic will have every fifth selected. Like systematic always has like an every kth element. So you'll always see like every fifth selected. Like we would talk to every fifth student at the dining hall or something. That'd be systematic. Good guess is Jesse right there. You said we are stratifying on time and place. It's not clusters. Stratifying twice. Because we are acknowledging the differences between dining halls. So there's 5 dining halls. So we're making sure we take samples from each of the 5 dining halls. Each of the 5 dining halls are a strata. And then we are taking samples during the different times of day. And so here's the other strata right here. What key thing in clustering does this not have? Like, what will you always look for in clusters? Whenever we do cluster sampling, always look for this key element to know if it was cluster sampling. When we have clusters, we always do a what on the clusters, which this does not follow. When we do cluster sampling, we will always do a what on the clusters. Do I have the definitions right behind here? I do. When we do clusters, we always take all of the clusters. So we're not taking everyone from the dining hall. In nowhere does it say we're going to talk to everyone at Stokely. In nowhere does it say we talk to everyone at breakfast. We are just taking representative amounts from breakfast, lunch, and dinner from the 5 dining halls representatively. So this way we get a good view of how each group views breakfast at each dining hall, how each group views lunch at each dining hall, how each group views dinner at each dining hall. So this is meant to be representative, not meant to speed it up. We're just going to go in and find 50 random students at each time and speak to them. So although this says 15, you'd be like, well, but isn't that a cluster? If this was cluster, it would say something more like this, which would not be a good sampling method. There are 5, this is a bad sampling method right here. There are 5 dining halls. To understand what students think, we go to 2 of the dining halls and talk to every student at the dining hall there. So notice what is done right now. How the dining halls now are being treated as clusters, and this is not a good sampling method. So this is a cluster sample. But you would say, but there's variation between the dining halls. That's what you'd be like, wait a minute. Why would you just go to 2 of them and speak to all the students? The dining halls are not random clusters, which is kind of one of the goals, that the things are put into groups randomly, and the dining halls are not random clusters. Also, time of day is not random on what you get to eat, so this would be a bad sampling way of doing it. I mean, it is cluster sampling, but it's not a good idea. It's just a misusage of cluster sampling because you don't meet the criteria of things randomly being put into clusters. Is this making sense? Tell me what you're thinking to compare the differences right here where this was double stratification. Now, RIP PCB. That's where my wife used to work. So shouts to PCB. She would do the bakery stuff. Really quick story. Wonder if he wouldn't still be there. One time, and I have no problem if people take some extra cookies or something. Like you go to PCB, you're about to leave, you walk up, maybe you take PCB's not there anymore. You take like 3 or 4 cookies. You know, like, hey, that's fine. I mean, whatever, you know. But here's what this guy did. This guy, he took the whole cookie tray. The whole tray. Like I'm talking 100 cookies. You know, they're like lined up. They got them like in a row. He just took the whole tray. So the tray is something too. You're not supposed to take the tray. You're not supposed to take 100 cookies either. So we were just like leaving PCB, just do 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 do, and I hear someone, yell, "Hey!" Cookie Monster little goes there. So someone had like chased him down the stairs and yelled, "Hey!" And he's like just like jogging along, and with the tray of cookies, and you can tell like he's not supposed to have that tray of cookies. I mean, who take 5 cookies? Take a hey, take a few cookies. So he runs by me. I just like grab his arm like this. I just grab it and he's like, "Ooh!" And I was like, give me the tray. He's just like looks at me and I'm just like, he gives me the tray. You can take some cookies. He takes like a few cookies and I say thank you. And I hand it back to him. The craziness that I've seen. Just grabbed him by the arm. Those are my wife's cookies. She wasn't working. I think she was with me. I think she was like right next to me, and I was just like, "What is this dude doing? What's that guy doing?" Anyways, what other questions are there? So these are the different ways to do things. This is a bad way right here. I wouldn't do this sort of cluster sampling right here. This is a bad idea. Systematic is where we would say something like, we go to the dining halls and speak to every 5th student leaving the dining hall from a random starting point. That would be an example of systematic. And this is what you want to do right here, is you want to think of different ways, systematic. Then you could say right here, another thing would be, we go to UT and ask them to randomly generate 100 names of students that we will contact about their dining experience. What is this sort of, what sort of sampling method is this right here? We go to UT and ask them to randomly generate 100 names of students that we will contact about their dining experience. What would this be? And this is where you have this sort of idea down. That's simple random, yep. What would be your sample frame? So we could say here, what, because we're reviewing sample frame 2, what is the sample frame in this question? So what is the sample frame in this question? Yeah, it is, because that UT has access to everyone. So it would be all UT students. So all UT students, because UT has access to all of them. So we go to the dining hall. So what is the sample frame here? What is the sample frame? What is the sample frame here? We go to a dining hall. What is the sample frame here? Remember, sample frame is everyone we have access to sample. So you just have to think theoretically. Yeah, Haley, yep. Students, well, wouldn't be every 5th student. So as long as they talk to us, they'd be the sample. But every student, so the reason this would be every student who is leaving the dining hall during that time, because theoretically they could be the 5th student. Does that make sense? So what is the sample frame? Because think about it, if we're standing outside the dining hall, then we could theoretically speak to any of the students leaving. So technically, you could probably expand to anyone at the dining hall or students who generally go during that time frame. But your sample frame would just be the people who could technically be every 5th student, because that's what you're sampling from in that moment. Like, you still are interested in the population, all UTK students, but the sample frame is going to be every student leaving the dining hall during that time, because they could technically be in your sample. So the sample frame is what is possible to be in your sample. Does that make sense? Now, when we go to the registrar, we could talk to everyone. So what is our sample right here? This is a not too hard of a question here. What is our sample? So what would our sample be right here? We're bouncing around between the questions. And this is a good review. These are good types of questions to know the differences between. Population is always the big thing we're interested in. Will the sample frames be the same? Oh, we'll do the cluster one here. Well, and good questions right there. The 100 students. Yep. as long as they speak to us. Like there's a thing called non-response bias if they don't talk to us. So with the cluster one right here, let's take a look. What is our sample frame? Okay. So technically, okay, so be careful on this. This one's, yeah, good seeing you here, Adam. Okay, so what is the sample frame right here? There are 5 dining halls, and this is not a good sampling method, but to understand this, what students think, we go to 2 random dining halls. So the sample frame is what is theoretically possible. The sample frame is what is theoretically possible. Is it theoretically possible that we could have spoken to anyone at any of the dining halls? We're going to go to 2 random dining halls and speak to everyone there. So it would be all students who are at the 5 dining halls during the time. Because we could have theoretically chosen any of the dining halls. Apparently spelled that way. So we could have selected any of the dining halls. Now the sample would be what? Given we don't have non-response bias. The sample would be what right here? It would be all students at the 2 randomly selected dining halls. I thought I had 2 ends. So the key difference here is the sample frame is what is theoretically possible, because it's theoretically possible any of the 5 dining halls could have been chosen, but the sample is only going to be the ones we actually get information on. And once again, we are assuming that they actually speak to us. There is non-response bias, so all the people who respond from the 2 randomly selected dining halls, all students who respond. So we should add that in. But that's very key right there. The sample is going to be all the students who give us information from the 2 randomly selected dining halls, and we're trying to collect data from all the students. Is this making more sense right here as we do practice over it? The sample frame is just like what is theoretically possible. So it's theoretically possible any of these 5 dining halls could have randomly be selected. So with that, we had the possibility of getting any student at the 5 dining halls. This here is the best way. And you could probably summarize it this way. So this is a multi-stage stratification twice. This is a really good sampling method. So what is the sample frame here? And just think about what you'd have to say, and then there's probably a good way of summarizing it. We're saying there are 5 dining halls. If there's a 6 or if there's 4, I'm sorry, in my example, I'm pretending UT has 5 dining halls. And we've got breakfast, lunch, and dinner. So think about what you're basically having as a sample frame right here and why this is so good. Like as you talk over it, you'll be like, oh, wait a minute. Because there's a long answer and then there's a short way of saying it. I might do the long answer first and then we'll think about what that implies. So the sample frame would be what? And this is who could possibly be sampled. And I don't know if Reed re-answered or... so the long answer here, I'll do the long answer, is any student at one of the 5 dining halls who is eating during breakfast, lunch, or dinner. What does this sound like to you? Any student at one of the 5 dining halls, like any student at any dining hall, or a student at any dining hall who is eating breakfast, lunch, or dinner. It almost sounds like students who eat at the dining halls. Yeah, any student that's eating, we really have a good sample frame right here that's representative of the population. That's why this one is such a good one, because students who go to the dining hall to eat, yeah, like any dining hall, any time frame generally, like we're going during the major time frames. Or we could even specify that, like if we're being very specific, we'd be like during the major time frames, and we could say at the time frame we were collecting data, but we collected data during the breakfast time, the lunch time, the dinner time. So we acknowledge that people will have differences in their views because of that, and differences in their views because of where they're eating. So that's why we stratified on that, because that's an important key difference. Then we have here, what is the sample? And this we can be very specific on again. Sorry, I just joined. If you're done with the question, you can do the one percentiles on with Z-scores. Yeah. Which one? Is it a test question? Kristen, thank you for asking. you want me to come up with a question or a practice test question, whichever you like? So the sample right here, we can be very specific on. What would the either or? Cool. I might come up with my own. And remember, we do have the practice test, and the review has me going over it. Come up with one, you bet. And do remember, we do have. I look at the views on videos, and don't worry, I don't get money for the views on a lot of these videos. But like a lot of people are not watching like the speed runs or the practice test videos. So there are the practice test videos. I'll show those here in a second. But there's the practice test videos and all that good stuff right there. So what is the sample? The students selected, or the 50 students selected at the different dining halls during the different times. Total of, so it's 15 times, that's 750 students. So because there are 5 dining halls and 3 times, 5 times 3 is 15. 15 times 50 is 750. So this would be, and this is kind of the best example right here. There is just one practice test. I think maybe I heard that the SI leaders might have some, but we've got here, there we go. The practice test review has all this right here. So once again, like I said, I'm like, no, people are not checking out like the correlation review. Where we go over here, and oh man, it put auto timestamps in here.
There's one outlier circled in my plot.
And you can see where we go over like z-scores, the empirical rule, percentiles on the curve, all this good stuff right here. So if you're wondering how to solve a lot of these, I've got the videos going over how to get each sort of answer and showing how we solve them, especially for different questions. But we'll come up with our own right here. There's one done by the SI leaders. Yep. So check those out, and let's do some 68, 95, 99.7. Good review of the sampling methods right there. Okay, so we want to be able to identify what is going on with an applet picture. So Stat Tool 1, Chapter 5, Normal Curve Review. I'm going to go over to the David M. Lane because Terry often uses pictures from it. I do love our applet though, but the key is that you wouldn't just know one applet. You have to know how to understand and interpret any sort of kind of distribution picture. What do we have on the screen right now? Very, very clearly, these are what's on the screen. So immediately you should identify, I am seeing what's on the bottom of the curve right now. Because it's centered at 0 and has standard deviations of 1. Those are all z-scores. We know they're z-scores because the standard normal curve, that's what this curve is called, not just the normal curve, but the standard normal curve, has a mean of 0. Hence, this is at the center. If I change it, it'll change the center. So I wanted 100. There we go. And then the standard deviation of 1 it had previously, but we can increase that, and that's the spread. So we say it's normal shape with center 0 and spread 1, and that is called the standard normal curve. So when we do problems with this, we can take a look at some of the possibilities. Now, if I were to tell you that the Stat 1 exam, had a mean of 80 and a standard deviation of, let's say, 8, and you made a 92, what percent of students did better than you? So the Stat 1 exam had a mean of 80 and a standard deviation of 8. What you made? What percent of students did better? Yep, we can do that, Tyler. All right, and we can use estimate first with the empirical rule. Then use the graphic to find. Okay, so I first want you to estimate with the empirical rule and then use the graphic to find the exact answer. So first we are going to estimate with the empirical rule. What might you figure out immediately? So let's start marking the question. Tell me based on the colors what everything is in notation. Notation is going to be super important for later, and please write down the notation. If you don't know what these things are, write them down as we talk about them. So there's only a little bit of notation, maybe maximum 20 things for notation. I know 20 is a lot. Close read, close answers. Close, very close. Very close answers, Reed. So what is the notation right here? Anyone know the notation for this? Like what is yellow, what is green? Yep, Reed, that is correct. Jesse and Reed got it now. So what is the notation for this? And we'll follow through on solving this. And great job. We got 3 more points. Good practice, Reed and Jesse. I'm excited for how you'll do on the test. So we have mu. Which one's mu? Mu means mean. So that's mu for mean. Mu for mean. And the standard deviation is 8, which we usually mark as sigma. And then 92 is the observed value. So that is our score, our observed score. So y minus mu over sigma is z-score. So we have here 80 observation. Nope. We have here... We have here 92 minus 80 divided by 8 equals 1.5. What do you notice immediately about this? What do you notice immediately about this? What do you notice? And we'll show how they got the other answers here in a second. What do you notice? (92) has a what? (92) has a z-score of 1.5. So the z-score right here of 1.5 is for 92. 92 has a z-score. It is the, well, it's not the 92nd percentile. It might actually be close to that. It is actually very close to it, ironically, but it's not the 92nd percentile. That is your score of a 92 has a z-score of 1.5, which has some similarities just by happenstance. So right here is 68% of the data, and 68% has 32 total outside, and 32 cut in half is 16%. Then we have 95 here, and 95 outside has 5%, cut in half is 2.5. And this is where the answers that Jesse and Reed came up with were for between 16 and 2.5. Great job, Kristen, right there with the z-score. So the answer is between 16 and 2.5 is what we're looking at right there. Now, when you think about this, you actually want this area right here. How could you get that area right there using the graphic? So you know your answer has to be between 16 and 2.5. How would you get that answer over there, that green area? How would you get the green area? I believe it is that, Reed. Correct. And it is that because this is 100 minus 93.32 because you want the other side of it. So that's showing you below 1.5 is 93.32% of area. And great job, Reed and Jesse right there. And great job, Tyler. So we were able to estimate it. The answer is 6.68. And that is between these numbers, which we said it would be. So these sorts of questions right here, especially we just did the empirical rule, as though the question said first do the empirical rule to take a estimate and then solve it using the applet picture below. So we were able to get it. And Reed and Jesse, what are your thoughts on these? Like, I know a lot of people have been working really hard on these, but this is just an example question right here where if you get it down, it's like, wait, I can do these. I know what it's showing me. I understand the information being presented to me, and hopefully it gets quicker as you do it. That's the goal, is like you get to the test and you're like, I've done a lot of these. This is easy. Normal curve stuff. Give me those normal curve questions. We'll do another version right here. I feel computable. Computable. So yeah, competency. Nice. We'll change it over to this, and let's go here and say your test score is in the top 10% of test scores. I've done this one a lot. This is a common question I just use repeatedly to say your test score will do the same sort of distribution, or we'll change it. The test had a mean of 75 and a standard. No, we've done 75 so many times. Yeah. Okay, I first want you to estimate using the empirical rule. So once again, we're doing empirical rule practice on this problem too. So don't worry about solving it yet. I first want you to estimate using the empirical rule. Comfortable, there we go. Can we cancel the exam for the Pascal game tonight? Sorry, Reed. So I want you to first figure out the estimate using the empirical rule. So what would you do here? And this problem is a lot like our previous problem. What would you do if you get a picture like this? I see where you're going with that, Jesse. You're on the right track. That's not quite the score. Actually, I think ironically your answer is correct, but it's happenstance. So what we would have right here is we need to mark below it. We would put right here 80, 85, 90, 95, 75, 70, 65. Now, when we think about the top 10%, I see where you're going with this, Jesse, or the 90th percentile, that's what you have right there, you would be somewhere where? Between what and what? And then I'll show how we're getting this. It actually relates to the last problem we did. If you have your work from the last problem, you can figure out what this has to be between mathematically. So where would you be between if you're in the top 10%, which is the 90th percentile? Double check, Reed. Your score needs to be between what and what? So only use the numbers on the curve. Your score would have to be between what and what? Your answers are technically correct, but we can give a smaller interval. So from our previous work, we found out that 68% is between here. So what does this represent right here? Just tell me what that means. Yep, Jesse, that is correct. Yep. So what is that right there? Just tell me what I've circled. And the reason we did that is because that's half of 32, which is the remaining area. But what have I circled right there? That is the what. The what. The top 16%, exactly. And then this right here is the top 2.5%. So it stands to reason top 10% is somewhere right around here-ish. And I chose that spot for a reason. The top 10% is somewhere around there. So it has to be between 85 to 90 just by empirical rule checking of it. So we know that the answer is somewhere there. And with that knowledge, let's look over here at this side of the curve. What do we see right here? We currently know the what for the what. So we know the answer has to be between, great job, Tyler, right there. We know it has to be between these values, and we currently know the what for the what. So here's what we are currently seeing, and this is what we have. So what are we seeing right here? The what for the what. So make sure you know it's on a curve with a mean of 0 and a standard deviation of 1. The z-score for the bottom 10%. So if this is the z-score for the bottom 10% and it's z equals negative 1.282, then what would the z-score be on the other side of the curve? What would the z-score be on the other side of the curve for the top 10%? And if you look really closely at it, you might see what it's going to be as best as I could draw. It's going to be 1.28 because it's just going to be the positive version of the number. And we can confirm this. We don't get to use the applet on the test, but we can confirm this if we go over here, not to that one. I keep slowing down my mouse. I gotta stop doing that. and we go over here and we go to above, and we can see it is the z-score for the top 10%. So that is the z-score, and great job, Hannah, right there. That is the z-score for the top 10%. And now we go back here and we say, well, what do we do with this? With this information that we now know where the top 10% is, what do we do with that? Well, what does the z-score tell us? What does a z-score tell us? What does the z-score tell us? Like, what do we know about this? And Jesse looks to have the answer right there. Great job, Jesse. And see, you can check because you're like, well, that's between 85 and 90. That's where I thought it would be. So you can check your work a little bit to be like, does that even sound reasonable? It does. How many standard deviations you are above or below the mean? So a z-score is literally, if you go to the mean and you go add to it, the z-score times the standard deviation, you will get the observation. It's a reworking of the formula observation minus mean over standard deviation equals z-score to just where you're solving now for z, or solving for y instead of z. So you can see right here the y has been solved for. It would just work that you go and you multiply the standard deviation over here, and then you would have the standard deviation gone because you multiply both sides by it, and then you would just add the mean to the other side. So if you add the mean, go plus mean, well, plus mean to both sides is the y. So it's a reworking of the formula, observation minus mean over standard deviation. So now since we know what our notation is up there, we're solving for the observation, which is the value right there. And we're going to go right here and say Jesse solved for 86.41, which is the answer, is equal to the mean plus the z-score, which is 1.282 times the standard deviation of 5. Solve through and get the answer right there. And great job, Kristen and Tyler, right there. So is it making more sense? These are just many, many ways to do the questions right here. We could even confirm our answer. Like if you come up with your own versions of this, you could just go here and then put in the numbers, and you could confirm your answer right there. 86.41 is the answer, and we've shown that we can solve it without the applet, but just getting information from an applet picture, which is kind of key to being able to solve these. We want to be able to solve any sort of, like, if we get partial information, and there's a lot of practice test questions right here where I show, like, oh, if you are given the opposite side of the curve, then you could find the other side of the curve. I'll do one just like that one. Let's say you score in the bottom 20%, then let me see here. We'll do bottom 21%. Sure. And just report as a whole number. You score in the bottom 21%. You can solve this one really quickly. Report a whole number. Report as a whole number right here. If you understand a lot of rules about this curve, this is a super quick question. So let's write this out. The curve below shows a test distribution where the mean was 80 and standard deviation was 10. You scored in the bottom percent. What did you score rounded to a whole number? Who can do this one really super quick? A bottom 21%. Can anyone do this one super duper quick? Say, how would you do it that quickly? Oh, I'll show how to do it. We'll show the quick tricks or the understandings that we would have. So what are we currently seeing? We're currently seeing the top 21%. So we want the bottom 21%. The rule of symmetry is going to apply right here. We'll see if anyone gets it. I'll solve it in about 10 seconds. But does anyone have a guess? Round to a nearest whole number, what you scored? 72? That's right, Jesse. Yep. Just take this right now and round it to a whole number. If you take this number right here, round it to this, then you would say that going up from the mean, it's 8 above the mean. So you would go down here to the other side of it, and you would just go 8 below the mean. You'd go minus 8 instead of plus 8. So 80 minus 8, or yeah, 80 minus 8 is 72. And that's the observation right there. So that's just the rule of symmetry. And you could carry decimals and stuff like that. You're welcome, Reed. So, and Hannah, great work there too. Is that making more sense? That was a quick solve on one that's kind of like the practice test. But if you just round it to whole numbers and you say, well, the top 21% is at 88, then that's 8 above. Okay, so what? Good question, Tyler, right there. So the top 21%, this is the top 21%, and the bottom 21%, have a symmetric distance away. Does that make sense? So this is the key right here to solving this, is that the top 21% is just as far above the mean. So it's just as far above the mean as the bottom 21% is below the mean. So now, if the top 21% is at 88, how far is it above the mean? If the top 21% is at 88, how far is the top 21% above the mean? Yeah, once you see it, you're like, oh, okay. And you just have to like solve a bunch of these and be like, okay, then that has to be 8 below. So all we're doing right here is just saying instead of going up 8, go down 8, and then you find the answer. So it's once you see it, it's like, oh, okay, I see what's going on. And that's a lot like one of the practice test questions, but the more you see these, the more you understand how it works with rules of symmetry, the better you get. We could do a question like this too, though, that says, here's another one. Use the 68, 95, 99.7 rule only. There are. Yep. We give applet pictures on the test, so you have to know how to use the applet pictures. And we also give questions like this where you only use these rules right here. So this means only use these rules. So here we go. The test had a mean of 80 and a standard deviation of 10. You scored a 90. What percentile did you score in? Can anyone get this one really quickly? So the first thing you'd want to do here is draw this out. You could also start solving certain things about a 90 and no information. Get this very quickly. So I'll write more questions based on this. So we'll do the first question right here on using this data. And so there's question 1. Use only the 68, 95, 99.7 rule only. Who knows this one? What does percentile mean? What does percentile mean? So to solve this, you have to know what percentile means. It is the 84th. That is correct. Percentile are the amount of students who scored below you. So for this one, we'd want to mark the curve here at 0, go up 1 standard deviation, which means we're at 80 at the center and going up 1. Now, we can do the -1 right here, and between here and here is 68% of the data. And with 68% between, that leaves 32 outside. Cut that in half to each side. And think about this. If this is the top 16%, then it has below it 84%. And that is currently where we are at. So we're at the 84th percentile right there, because 84% of the data is below here. So that's kind of the key to that question. So good stuff right there. Good practice where you can draw the curve, find the z-score. And the more you draw the curve, the better you get at these. So please attempt to do that. Always attempt to do what I do. Watching me is one thing, but writing it down is another. It's going to help you a lot more. What percent of students are expected to score between a 60 and 90? There we go. What percent of students, can we do another one? Yeah, of course. We're doing as many as we can. What percent of students are expected to score between a 60 and a 90? So what percent of students are expected to score between a 60 and a 90? How would we solve this one? Take a moment, and once again, this is for you to solve it. Your time here to solve it and see what you get. So what percent of students are expected to score between a 60 and a 90? It is 81.5. Great job, Hannah, right there. That is the right answer. Let's show how that answer is obtained right here. This is a trickier one of the harder ones we can do. I'll do another hard one here in a second. We draw out the curve. And what are the z-scores for this? What are the z-scores for this? Between what and what z-score? So I'm just asking additional questions right here while I draw the curve. So you want to draw your curve with the mean and the standard deviation. Great job, Jesse, showing some of the work right there. And so we have here 80, 90, 100, 110. A lot of bonus on the exam, at least this one theoretically. Then we go right here and we go here to here. So there's a lot of ways to solve this. One maybe easier way for people to solve it is to do the following. How much is this worth right here? So the whole thing is worth 68%. So how much is the green worth? How much is the green worth? Because the whole thing, like this, is worth 68% between the black arrows. So how much is the green worth? Just this area inside of here. 34 because it's half of 68. So this is just one way to solve it using just the full numbers. So that's 34%. And now we want to find this area over here, which how can we find that area? So now we want that area over there, and that area will be what? Mathematically speaking, that area will be what? So think about how we can get that area. I need to put that into a different spot. How can we get that area as best I could have drawn it? That area right there can be obtained how? 95, and what of 95? What are we going to do with 95? Because 95 is the whole area. Whoa. 95 is the whole area, half of 95, exactly. So this would be 47.5, and then we just add together those two areas right there. And this is probably one of the harder ones to solve because it's not a nice, neat number on the empirical rule. And there we go, Hannah, great work right there. 95 minus 50 wouldn't exactly do it. It'd be half of 95 right there. So that's going to be the percent right there because 95 is the area between here and here, and half of 95 is going to be half of the area. So lots of ways to solve this. Just as long as you get the right answer, that's what matters. So good stuff, and we'll do another one. We're just trying to do as many as we can do. So what percent of students are expected to score above a 110? What percent of students are expected to score above a 110? What's the first thing you might do with 110? What is the first thing you might do with 110? If you see 110, you might immediately do what right here? And I'll do another difficult one. Great job. Hannah already has the answer. Careful, decimals on it, Sydney, and you'll be correct. So make sure this one is a decimal format. It has the 0.15 after it. And the reason we're able to get this, the first thing you might do with 110 is you might find its z-score. The z-score for 110 is 3. So we go right here to 1, 2, 3. And we go down. And then we check it out right here. 110 is over here on the curve we've drawn, and we want the area above here. So between here and here is 99.7. That means 0.15 is above here because that's half of 0.3. What percentile is this? That is the what percentile on the curve. That is the what percentile. Just checking our knowledge of percentiles and how percentiles work. So that right there is the what percentile. Careful, careful. That right there is the what percentile. What percentile is that on the curve? Not 99.7th percentile. Close. It's close to that. 99.85th. Because percentile is the area below that point. You could also do 1 minus the area above there. And the percentile is 99.85th percentile. That is the percentile. Here we'll use the empirical rule again. Great job, Tyler, right there. Give the smallest interval possible for the percent of students who scored above a 102, i.e., as in between blank percent to blank percent. Okay. So what would this be right here? Give the smallest interval possible for the students who scored above 102. What might you do with 102? I want to repeat this. It doesn't ask you to do this, but what could you do with 102 right here to understand it a little bit better? Excuse me. What could you do with 102 to understand it a little bit better? What could you do with 102 to understand it a little bit better? What could you do with it? We can always take an observation and turn it into a what? So we can take our observation right here. Well, we can mark it on the graph. That is correct. Good answers right there, Tyler. We can take the observation and turn it into a what, though? Z-score it. So it's a z-score of what? We're going to do it just as the z-score this time, kind of knowing where it would be at. It's a z-score of what? 2.2. Yep. And you can mark the numbers below to make sure you know it. So we'd go right here and say it's at 2.2. So what is it's between this percent to this percent. So we're trying to estimate this area right here. That's the area we're interested in, but it's not directly on an empirical rule number. Great job. Jesse has the answer right there. It's using a lot of our previous knowledge from previous questions, where between -3 to +3 is 99.7. Take the 0.3, divide by 2, and you get 0.15 above here. And there would also be 0.15 below there, technically. And then we go right here, and we go to the 95%. And 2.5, because 5 divided by 2. How's this looking? Jesse got it right there. Are people feeling better about these? I know we're doing them really quickly, but we're just trying to show how the rules can be used, and then marking your graph is going to be key. I put that blue arrow a little bit too close to that. We do want the blue arrow directly over the 2 standard deviations, because that's where it's above 2, and 2 is a little bit to the left of that. Oh yeah, so we could do percent. For this, it says interval possible for the percent of students who scored above this. So this question could have read, so this is the percent of students who scored above this. It doesn't say percentile right there, but it could say give the smallest interval possible for the percentile of students who scored who had a score of 102 on the test. So now give the percentile. This is very similar work right here. However you want to phrase it, Tyler. So Jesse, try this, and Hannah, try this. This says now give the smallest interval possible for the percentile of students who had a score of 102 on the exam. There between the what and what percentile. Very similar work. Our drawing can help us find the answer to this, but this time it says give the percentile. That is correct right there, Hannah. That is exactly correct. So all you're doing is taking Jesse's answers and subtracting from 100, because if you go below this point, you would see right here that it has 99.85 below this point. And then below this point is the remaining 2.5 down there, which we don't have marked. But that is how you could do it right there. So lots of ways to do this. This has been a little bit more advanced. Sometimes we teach to a higher level, but if you're solving these pretty quickly, even though our z-score is 2.2, we still use 2.5. 2.5 is the amount of area above 2 standard deviations. So the z-score of 2.2 is the value over here that we obtained using the formula observation of 102 minus mean of 80 or standard deviation of 10 is the z-score telling us where the observation is at. So the 2.5 relates to the amount of observations above 2 standard deviations. The z-score is just how many standard deviations above the mean our observation is. So the observation of 102 was 2.2 standard deviations above the mean. And that's where 102 would be at right there. And that's at a z-score of 2.2. So I should have wrote them the other way. I should have wrote 2.2 and 102 down here. Is that making sense, Tyler, right there? So that the observation of 102 was 2.2 standard deviations above the mean. The percent of scores above 100 was 2.5%. The percent of scores above 110, which is 3 standard deviations, is 0.15. So the 2.5 is the percent of area above that mark right there, the one right here. That's 2.5% of observations are above a 100. We observed a score of, and good to see her neck, we observed a score of 102, which was 2.2 standard deviations above the mean. Good stuff. Well, that's a lot of those questions. What else should we do? We've done a lot of empirical rule questions. What other questions? Hey, Isaac, good to see you here. And make sure to check out the review. The problem is I think a lot of people review the day of the test, which I would highly suggest reviewing the weekend before the test. Then you come with questions. True falses? Yeah, we did some during class, and we'll try to do some for like chapter 1 and stuff. See right here. Check out the review. I just posted again in the chat. Check out the review. It's pretty interesting to see like all the it's like a lot of the review videos had like 30 views in the last 2 days, and I'm like, that means like, oh no, we got 1,500 students. It means like, what percent? 2% of students have watched the videos. Ah! So the videos are meant to help you understand like reviewing the chapters, practice tests, and chapter reviews. I try to make them concise, so good review stuff, I think. Good usage of time. Let's do some true false. No worries. Oh, good job, Tyler, right there. Okay, how empirical? A few? A few? Good question. I don't know exactly how many. 107, 103, stat 201, true false. Okay. Let's go through here and try some true false. And let me pull up the ones from yesterday. Okay. So these are true falses we came up with yesterday. We were just doing it off the top of our head. I didn't look at the test yet. Well, I mean, I've seen it, but I wasn't looking at it to do this. So these are just ones we were just coming up with. If it's purple, it's false. If it's yellow, it's true. And we came up with a lot of these questions. You can pause the screen at any moment if you want to write these down. And we got down here to chapter 3. So let's do some true false for chapter 3 and ask a question like, stacked histograms have a quantitative y and quantitative x. That might be a chapter 4 question. Stacked histograms have a quantitative y and quantitative x. Thoughts on this? It's chapter 4-ish, but we'll kind of chapter 3 for a moment. Chapter 3 is chi-squared stuff. Stacked histograms have a quantitative y and quantitative x. So here's your hints. Stacked histograms have a quantitative y and quantitative x. This is, good guess right there, Sydney. This is false. Quantitative y and quantitative x are used for what? Quantitative y and quantitative x are used for what? Two quantitative variables, q, q, are used for what? A quantitative y and quantitative x are used for what? Scatter plots. Great job, Sydney. Good recovery right there. Yeah, more points in the chat. So scatter plots. Stacked histograms have a... Let me go to my effects screen to do this. So stacked histograms have a categorical x. You have to take a look right here for the stacked histograms. They have a categorical x. See, it says variable x on that side, and a quantitative y. So this graphic right here shows us that they are bivariate. We have two variables, and the histograms themselves are quantitative, but when you stack them, you're doing it on a categorical variable. Let's say right here, when looking at a mosaic plot, large differences in the conditional distributions are evidence of an association. So true or false? When looking at mosaic plots, large differences in the conditional distributions are evidence of an association. So we've got a lot of big words right here like mosaic plot, conditional distribution, and associations. True or false? True. Great job, Sydney, right there. This one is true. So this one is true, though. Let's take a look and see what it looks like visually and review what it means. So we'd go over here, and we need to go to all data. And let's do here analyze, and let's go fit y by x. We're going to see if gender can explain. Do we have broken bone on here still? Broken a bone. There we go. So we're going to see if gender can explain if somebody's broken a bone. Now, looking at this right here, we've got here males with yes. And if you hover over it, about 51% of males have broken a bone. We can pin that right here. So about 51% of males have broken a bone. And then females, about 42%, 41%. So look at the difference. It's not quite, but about 10% more males have broken a bone. So you might say here, males are a little bit what to what? This is the condition of female. This is the condition of male because we are within. It's not everybody. This is the marginal display of breaking a bone, like the percent of people total who have broken a bone. Actually, it's appearing on my other screen. Whoa, where'd it go? It's on the other screen. So I literally have to, there it is, look at that. So total 56% of people have broken a bone, but what about males? What would you say? Slightly more what have what? And this is evidence of somewhat of an association. So this is the margin, which is kind of an average of, it's not quite, it's a weighted average technically, but since there's almost 50-50 males and females, there are a little more females than males. So we could even go down here. Well, we can't display that one, but that's the marginals right there. 54% of our survey was female. 56% were male, rounding the numbers. But you'd say a little bit more what right here? A little bit more males have broken bones than females. And one way I like to really display this is if we were to give you a version of the test. So version of test. And we have A, B, B. And then we have outcome. And we have here pass, fail. And then we have the frequency of observations. And we have here, take a look at this display here. What do you notice about the version explaining the outcome? When it comes to the version and the outcome, what do you notice? You're welcome to version and the outcome. What do you notice? Whether or not someone got version A or B, what do you notice? So notice the output over here, and whether someone got A or B, it looks the exact same. So the condition of A, like for the students who had A, the same percent failed for the students who had B. There's no evidence of a relationship. Now, the stronger the relationship, the bigger the differences in the conditional displays. The conditional is within one variable right here, like given someone took version A. So if all of a sudden more people are failing version A, you're going to see bigger differences. So we could eventually get to a difference something like this right here, or even crazier like this right here. Now you'll also notice that A is smaller in the margin, which denotes that more people took B than A. But this would be very unfair if we saw this kind of analysis. We'd be like, wait a minute, a lot more people are failing A than B. So wait, what's wrong with A? Like over 50% of people failed A. We could do the mathematics over here and solve it to say there were 45 students who took A. And out of the 45, we saw 25 fail it. So that is 55%, and that's what this is calculating right here when you hover over it. You can see right here, it's going to say 55.56% is the percent that failed version A. So now there looks like a strong association between it because the differences in the conditional distributions. And we'd even reject the null hypothesis that there is no association. So if we use p-values down here, we would say, I reject the null that there is no association. I have evidence of a strong association. So really good stuff right there. Which document number are we on? Where did we put the true falses? Here we go. The marginal displays on a contingency table only display one variable at a time. True or false? The marginal displays on a contingency table only display one variable at a time. The marginal displays on a contingency table only display one variable at a time. This is true. If we take a look over here at a contingency table, where are the margins at? Where are the margins? The margins are on the outside. So when we look at a marginal display, the marginal display is down here. This is the marginal display of what? That is the marginal display of what? So I just need one word. Well, but it has total, but what variable? That is the marginal display of what? What variable? It is the marginal display of the outcome. So if you go down here, these are the outcomes where 35 students failed and 120 students passed. Then the other side of it is the marginal display of version, where we can see 45 took version A and 110 took version B. Does that make sense right here? So this traces over this way to the marginal display on the outside. So the marginal display just shows you one variable to say 45 students took version A and 110 took version B, or the other marginal display down here, and the marginal displays are in the margin. So the outcome is down here, and it's only showing us the totals for the outcome. So it's only one variable being displayed. Now, if I do this, what kind of display am I doing here by saying, of the students who failed, what amount took version B? That's a what display. Of the students who failed, what percent took version B, which is 10 over 35. So this is called a what display, like of the students who failed, what percent took version B? That is a conditional. So conditional looks within one variable at the distribution of another, where margin is literally the margins. Contingency tables also have a margin. Down here, you can see more students took B than A, and also more students passed than failed. It doesn't look at the other variables. It's within the mosaic plot that we see the condition of version A. You can flip it to get the other conditions, but that's the way it works. Okay. What else do we have? Stacked or segmented bar charts, along with side-by-side pie charts, can be used to display bivariate categorical data. Stacked or segmented bar charts, along with side-by-side pie charts, can be used to display bivariate categorical data. True or false? This is very true. And we can show it over here because we can make some graphics with it, where we go to graph builder, and we do side-by-side pie charts. I think we'd go here to we got to go to the frequency, right? Frequency down there. Did I do that right? Outcome. Put it in a pie chart. Oh, did I not put the frequency down there? I'm going to do it in a different way. All right, let me go to a different thing. That's a bunch of side-by-side pie charts. Let me go to the other data we had open right here, and let's go to graph builder, and go to gender, drop gender right there, go to pie chart, and then go to family income, and then we'll go right here and go to there. Oh, there we go. Look at those side-by-side pie charts. So there's a bunch of side-by-side pie charts right there. Not a huge fan of these. That's side-by-side pie charts. We could probably click the bars and get stacked bar charts. That's side-by-side bar charts. Not a big fan of stacked graphics. I've made a few in my day. So trying to think how to make them here. That's a mosaic plot. So it might be stacked. Ooh, don't do that. Looks horrible. That's a mosaic plot. It's just straight up mosaic plot. That's a looks like a heat map right there. Yep, so we can just make different graphics. You gotta be careful with what you make, because some of them are not going to make the data properly. You do get your grades back pretty quickly. I think we might have the answers hidden, but should get them back pretty quickly. Yeah, because I think people have already said to me, "Hey, I did a good job." They took it early. What else from chapter 3? We did some computation stuff. Well, this is true false we're talking about right now. Let's think of one more. When mosaic plots and contingency tables are ideal for displaying two quantitative variables. True or false? I hope low 80s, but then a lot of people get overly confident. They're like, this class is easy. It's easy. I made an 85 on the first exam. And then they're like, then we get to the second exam. We're like, what the heck are we even learning? Regression? What? This is false. Why is it false? It says it's ideal for displaying two quantitative variables. So why is it false? Oh, wait, I put the true color on it. Why is it false? Contingency table and mosaic plots are two categorical variables, as seen in the bottom right corner. And a scatter plot is quantitative, i.e. QQ straight enough, no outliers. Or if you have time on the x-axis, it's a time plot. Time plots are special case scatter plots. Chapter 2. And do check it out. Here's the chapter 4. Here, we'll put it on a new page. Here's the chapter 4 true falses. The yellow are true. The purple are false. Here's the chapter 5 true falses. Purple is true. Yellow is false. Put them on note cards for yourself. Once again, I'm coming up with these off the top of my head. They might match some on the exams just because there's only so many things to ask. So Terry, if you see this, I'm not trying to cheat. Just sometimes we accidentally teach to the test. So here we are with chapter 2. When data is skewed, the proper measure of center is the IQR. When data is skewed, the proper measure of center is IQR. I just joined, so I want to triple check. What all do you recommend having when taking the exam? Scratch sheet of paper, calculator, and your ID. Scratch sheet of paper, calculator, and the ID. Thank you, John, for that question. Jonathan, for your question. So what are the possibilities for center? 100 points right there for everyone following along and attempting to answer it. What are the possibilities of center? The possibilities of center are what or what? But wait. IQR and standard deviation are measures of spread. The center is median or mean. People are seeing it right. They're like, oh, wait a minute. Because if data is skewed, we did some data earlier. Here's where we did data earlier. The center of this data is the median. And Jesse has it right there. And then the spread is the IQR. The mean is the center for more normally distributed data, more unimodal symmetric. And then the standard deviation is the spread. So make sure to know that, and always notice that the IQR and the median are right next to each other, and the mean and standard deviation are right next to each other too. This is for more normal data right over here. This is more for skewed data because outliers are not going to impact these positions in the data. So tricky question right there. Yeah, I wanted that to be tricky because when you see skewed, you think, IQR is great. It would be true if we said something like when data is skewed, the proper measure of center, center is the median. That is true. The median is highly influenced by outliers. The median is highly influenced by outliers. The median is highly influenced by outliers. False. And you can check this by just coming up with two data sets. First data set here is 1, 5, and then 10. Next data set is 1, 5, and then 100. What is the median for both data sets? It's going to be 5 because 5 is the middle number. We can do a check on your median knowledge too to say what is the median of this data. What's the median of that data? That's a quick check to make sure you know how to solve the median. So here's question A, and here's question B. What's the median of question A and question B? And this one is false. The median is not highly influenced by outliers. That is a false. Really? I don't like to do it. Really? What is the median for A? What is the median for B? Trying to trick you. Checking your knowledge. That's a 1 over there on the far side. What is the median for A? What is the median for B? This is a check to make sure you know how to find the median properly. We're trying to hit as many questions as we can. We're just question. No one knows the median for A yet. A is the easy one. So what is the median for the data in A? Well, it's is it 1? Is it 2? What do we always do when we find the median? The first thing to do is to put the data values in order. So 1, 2, 10, middle number. So then notice B, and B is 2.5. It might be. I think it might be. So we have to go here 1, 1, 2, 3, 8, 10. There is no middle number, so we average those right there. With 6 numbers, you have to think we have 6 numbers, so the middle numbers between number 3 and number 4. We don't usually give you too many numbers. I like to create like a seesaw here or find the middle number, and you should see a symmetric amount below as a symmetric amount above. But that is how you solve those right there. Always make sure to put the numbers in order. That is a thing that just happens a lot. People forget to do it, and then they're like, no! I've had people make 98s on the test. Don't worry if you missed that. That is a very common mistake that is made. It's chapter 2, but go back to chapter 3 for a second here. Okay. When doing box plots, the highest point is 1.5 IQRs above Q3. Or let me even say point observation. When doing box plots, the highest observation is 1.5 IQRs above Q3. This is very clearly one of the two, true or false. Very clearly. I'm like giving some tougher questions, trying to trick the students who know some of the topics to see exactly. So what do you think, true or false? When doing box plots, the highest observation is 1.5 IQRs above Q3. Don't worry if you get it wrong. I'm going to throw points if you get it right or wrong. Boom, Jesse. That is, and Jesse explained why. Jesse said why. Jesse, that is correct. That is false. That is where the fence is. So we can have some interesting box plots. Like, one of the weirdest box plots you can get is if I ask people, how many yachts do you own? So this box plot right here for yachts is going to look the following way. Let's go to Anal or Graph Builder and just drop this in right here and do a, well, we put it on the y-axis. There we go. And then turn it into a box plot, and it just looks like a line. It looks like a line because every single number is in the same spot. The min is 0, the Q1 is 0. So that is, you can get outliers outside the fence. Exactly. So you know what's interesting, Jesse? Where's the upper fence on this one? This is such a weird question. I'm not going to do it for too long. I'm going to do a better example here with, let's say we go to a more affluent community that owns yachts. But where is the upper fence on this one? Where's the upper fence on this? The upper fence is actually at where? The upper fence is actually at 0 because it'd be Q3 plus 1.5 IQRs. So you know what would be interesting right here? When you think about it, what does that tell you? Owning a yacht would make you a what? Owning a yacht would make you a what? Think about why it makes sense. You'd be like, well, yeah, owning a yacht would make you a what? So owning a yacht, if someone owned a yacht in stat 1, you're like, yeah, I own a yacht. You're like, really? Well, then you're a what? Instantaneously. Because there's really no variation in the data, you're an outlier. So we'll change this over here to exam scores. Yep. So that's interesting right there because there's so little variation down here that even the owning of one yacht makes you an outlier. And let's go over here to exam scores, which now we're not going to be zeros. On these exam scores, we're going to put in here something like 70, 80, sure, 80, 85, 82, 90. You can see the box plots start to build right there. 80, 75. No, we don't want 7. 75, 80, 85, 90, 90, 80, 80, 80. Okay. So now, why don't we see the median? Why don't we see the median right here? Why is the median missing? And look over here at the data. Can I sort this? Let me sort it, please. Don't say graphics being made from it. Really? It doesn't let you sort things where a graphics made from it. It's the same as Q1. So they're on top of each other right here. We could start to move it a little bit. There we go. There's the median at 81. So actually it's the average of those numbers. So there's the median. I know we're changing the data, but that just lets us see it. Sometimes values overlap, like percentiles overlap. So sometimes you would have here the median and Q1 are on top of each other. So very quickly, this one's very easy to find the IQR. What is the IQR for this data set? Super easy to find because of the way the numbers are. So what is the IQR, which is the range of the middle 50%? What is the IQR? Very, very easy to find for this. And I'm going to change the data because I don't want to do the math on the next part. 6.25. Because that's how far those numbers are away, the range of the middle 50%. So I'm going to change this a little bit right here. Is it this 85? Let me change it to 86. There we go. Well, let's change it to 90. Cool. Okay, what is the IQR now? This is a much easier problem. What is the IQR now? I love it. What is the IQR now? Very easily what? The IQR is the range of the middle 50%. So the middle 50%, which is the length of the box. You can also see it over here. It's just going to be 10 is the range of that. There's no value outside of 90, so 90 is the max. It's also Q3. So we've got a lot of overlapping values right here. So where do low outliers begin? Where do low outliers begin? So my question right now is, where do low outliers begin? They would be anything below what value? So the mathematical formula is, remember this IQR is 10. So it'd be Q1 minus 1.5 IQR. 65. Great job, Jesse, right there. So Jesse's just plugging in 10 right here, and the Q1 is 80. So it's 80 minus 1.5 times 10 via the formula right there to tell us where low outliers begin. So I'm going to take this value over here, change it to 65, and you'll notice it won't be an outlier yet, but now when I make it 64.999, it is an outlier. So the fence, which we do not see, is right here. Now, what does this area indicate between 75 to this? We'll call it a 64 to make it nice and easy to talk about. What does this area indicate right here between these points? Area indicate right here. What does that area indicate? A what in the data? Well, that's not the fence. The fence is a good answer. The fence is right here, and we never see the fence. It's just a graphical technique. So the fence is a graphical technique, which we do not see. They don't include them when we see it. It's a gap in the data. And good answers, Isaac, right there. We'll throw you some points. That's a gap in the data where there's no observations. There's just no one scored between this range. The fence, which we do not see, is right here. That just denotes where outliers begin and end. Well, within the fence, they're not outliers, and outside the fence, they are outliers. What is the range of this data? So what is the range of this data? It's about what? I'm trying to trick you. What is the range of this data? It's about what? Or it's exactly what? What is the range of this data? Trying to trick you. What is the range of this data? Trying to trick you. It is 26. 26. Yep. Because you got to include the outliers. So, and great answers right there, Isaac and everyone. So when we do questions, watch out for those outliers. That's how I tricked people on the Kahoot. Going back over here to this data. Here we go. Go to analyze, fit y by x, and let's go to family income and go to the weights of individuals. And which of these groups has the biggest range? So which of these groups has the biggest range? Is it middle, middle, upper? Which of these has the biggest range? Is it lower, lower, middle? Which of these? And maybe we'll get it closer again so you can see. Very easy to answer this question. Is it lower, lower, middle, 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 upper, or upper has the biggest range? Well, let's more people answer here. Very clear to answer. You can check your work down below. It is middle upper. And if you look just at the box plot, you'd be like, well, wait a minute. This one right here is longer, but this has more outliers. And you can see right here, the max to the min. Can I add another value? Column. Dang it. Well, you see, I could just do min and max. That's going to be a lot to, well, yeah, that's what I thought I would do. Oh, we do want that. I wish I could add in the range of it. But you could, if you wanted to, and take the time right here, only show someone the min and the max. And you'll be able to see a lot clearer with this. We'll do it. This is the neat thing about Jump is you can like edit your data down to show exactly what you want. So you could show people that between the min and the max, this is the greatest range right here for this group right here. Just look at the distance those numbers are apart. It's definitely because of the outliers, and it's really neat how it selects the data for you. What's even better is using this, you could actually go to table and go to subset and only get those individuals. So now we have only those 290 individuals, which are in the middle upper, and then you can analyze them. So that's really why Jump is so good, or data software, because you can easily select data and do analysis just by going like, let me take these upper class individuals and let's just go to table and then go to subset. And now you have all of those selected rows and you have the 40 upper class. So you could say, let's look at the distribution of upper class people and what's their credit card limit. Why not? What's the distribution of credit card limit for upper class people? $100,000. That's crazy. So, but a lot of people didn't have credit cards. There are 50% of students had, or of the upper class, which was 40 individuals, had a max credit card, which was of 0, which sounds like they don't have one. So really good work right there. We got chapter 1. Chapter 1. Where is there we go. Do a little chapter 1 here and then finish off. So chapter 1. Chapter 1. Let's see, or this is not in the right order anymore. quantitative variables must be real numbers. True or false? Quantitative variables must be real numbers. Quantitative variables must be real numbers. What are your thoughts? Quantitative variables must be real numbers. Very, very what? That is very, very true. Quantitative variables must be real numbers right here. They must be real numbers. So, nope. Good answer sitting right there. Quantitative variables must be real numbers. We can do the reverse, though, and say data that are numbers must be quantitative. So, data that are numbers must be quantitative. True or false? Data that are numbers must be quantitative. So, data that are numbers, this is false, because you could collect something like gender or state someone's born in as numbers. And so just because things are numbers doesn't mean they're quantitative. Like zip code is not a quantity of zip code. Always think of examples of like why it's false or why it's true. But if something, quantitative variables must be numbers because it's a quantity. So that's a key part of it. Quantities must be numbers, where things that are numbers aren't necessarily quantities. Like my zip code 27106 is not going to be a quantity of how much zip code I have. And so what else do we have? Ordinal quantitative variables are groups put in order. Are categories put in order, let's say. True or false? Ordinal quantitative variables are categories put in order. Ordinal quantitative variables. True or false? This is very, very what? I think people are, I throw out points for all the answers. Don't worry. You can put this is false. Ordinal variables are what kind of variables? Ordinal variables are what kind of variables? Ordinal variables are a special kind of this type of variable. Ordinal variables are a special type of this type of variable. Ordinal variables are categorical. So there's two types of categorical variables, ordinal and nominal. We can actually do them in Jump. If you want to do ordinal and nominal in Jump, you could actually go here to something like family income, and you can turn it. We rarely use this, but the ordinal variable is to turn it right here and go to ordinal. See, ordinal and nominal, and continuous is quantitative. So right here, it's now an ordinal categorical variable. It just has the green next to it. So you notice the green bars have been put in order, making it an ordinal categorical variable. It still analyzes the same way. If we go over here to look at it, it still makes a bar chart for us, and it's just been put in order. This is not a histogram. It's not normally distributed. You could say it's centralized around this. It does have order to it now, so it is centralized around that area, but we don't really talk about this with like normally distributed. We would say it's centralized around middle and middle upper class, and maybe a little pull towards the low side right there. I mean, I don't know. I don't like using the words like normally distributed for categorical data, but this is ordinal, so it does have some order to it, where things like what hand do you use, that's nominal. Nominal means has no order to it, so there is no order to like both left or right. So definitely now we would never say anything like normally distributed because the bar order doesn't matter here. It's just been put in a random order for us. So this is a nominal categorical variable because there's no order to it. And then this other one right here with family income level has order, lower to upper class has an order to it. So we wouldn't say an ordinal quantitative variable, ordinal categorical variables have order to them. That is the true statement right there. Ordinal categorical variables have order to them. That is true. Trying to think what else. Might take a short break right here. There's a lot to cover. We covered sampling earlier on, so check out the sampling parts of this. With that, I'm going to check some emails because it's a busy day with the test. Good luck, everyone. We got true falses here to check out. Remember, check out the review videos, which we have pinned right there. And good luck on the test. But let me know if you have any questions or any problems. I'll be answering all the emails. I'm going to go check them out now because I got class coming up here and we've got emails. You're welcome, Isaac. I'm glad this was super helpful. Until then, bye for now, everyone. Bye. You're welcome, Johnny. 5 hours. We've almost got these new intros ready. We're almost there.
This has been going for like 20 hours. This ends now.